We're going to talk a little bit more about basic probability, and we'll start with empirical probability. We ended the last part with classical probability. That's the type of probability you're most familiar with. Empirical or statistical probability is based entirely on observations. So I went out and I counted the number of, red cars in the parking lot, the number of gold cars in the parking lot, and based on the number of cars that I found in the parking lot of a certain color, that's how I'm going to figure out what the probability of finding a red car in the next parking lot is all about. So the probability of some event occurring is equal to the frequency of an event, how many of those things did I count, divided by the total number of things I counted. So a travel agent, they used to have those. A travel agent would make plane bookings or cruise bookings for you. Every time they make 50 reservations, so for every 50 reservations, 12 of those reservations will be for a cruise. So she observed that actual data. So what's the probability that for the next reservation she makes, it will be for a cruise? Well, based on what she knew from past observations, she's going to take 12, that's the frequency of event E, and divide it by 50 to get 0.24. Here's a relative frequency chart. If a car is in good working order at a factory, let's say we call it a good car. If it's in poor working order, that car is known as a lemon. So notice that we've got 500 cars here that we're looking at. 10 of them were lemons. They were in bad working order. 490 were in good working order. So to find the relative frequency, just like we did in chapter 2, we take 490 and divide by 500 for the good cars, 10 divided by 500 for the lemon cars. Notice our sum has to equal 1, just like it did with relative frequencies. So what's the probability that the next car we just randomly pick is a lemon? Well, that's our relative frequency. 490 divided by 500, which is 0.98. Done. How about this? Here I've got a frequency distribution that is delineated by ages. There's 30 people in class, so the sum of all of my frequencies has to add up to 30. And we're just going by ages. So if I randomly pick one of those 30 students, what's the probability that that student is between 26 and 33 years old? So we look at this line. Notice that there are 8 students in that category, and 8 divided by 30 is 0.267. Notice we went out to 3 decimal places. So the probability that a student is between 26 and 33 years old is 0.267. Now, the law of large numbers is something we need to come in or to keep in mind. If I were to ask you, what's the probability that in 10 flips of a coin, I would get 5 heads? You should answer 50%, 0.5, because you have a 50-50 shot at heads or tails. But what actually happens when you flip the coin 10 times may not be a nice, even Steven 5 heads and 5 tails. And that's where the law of large numbers comes into play. I may not see a 50-50 split in 10 flips of a coin, but I should be getting closer to that 50-50 split the more times I flip the coin. If I flip the coin 50 times, I still may not get 25-25, but I'm closer to a 50-50 split than I was with 10 flips. If I flip the coin 500 times, again, it may not be 250 for heads and tails each, but it's going to be a lot closer to a 50-50 split than my 50 flips or my 10 flips. So the more I conduct an experiment, the closer those numbers get to what's called theoretical probability. And that's what this example is all about. And that's why we can use probability to make predictions. No, we don't actually flip our coin 1,000 times to prove that the split is 50-50.